Today's experiment is about the pH, and we'll learn about the pH and the buffer. So let's look at the pH first by definition. What do we mean by the pH? So here it is. Let me just take. Somebody will tell me what we mean by the pH. Okay, so the pH is what? Minus log, correct? The the hydronium ion, the proton ion. So this is the correct pH definition. The old days we have the pH is equal minus log H plus, and that's wrong because this one here is not available to us in the solution, does not exist really. Okay, this one does not exist. Hydronium ion, what's happened is as soon as it's produced, it will come and then react with H2O to produce H3O plus, and H3O plus called hydronium ion, and this is called here proton ion. Okay guys, so let's look at the pH is minus log the concentration of hydronium ion in aqueous solution, and the whole thing here, the pH is always related what in aqueous solution. Now if we don't have aqueous solution, we have organic solution, then the whole story will be different. Then we have a different type of scale. This pH here goes, the scale of the pH, I'm taking this one out and you can look into this. The pH scale here goes from 0 to all the way to 14. But the pH, this is aqueous solution. Now the pH of the non-aqueous solution goes from whatever 0 to all the way 50, whatever the scale is, larger scale. And they use Hammett, they call it Hammett equation, they use it, but we are not interested. That's non-aqueous. The organic compounds, acidity, basicity will be a little bit different from the aqueous solution. We are interested in the aqueous solution. We are not interested in the high scale pH of the organic non-soluble in H2O acidity and basicity. So let me take this one here, scale, and then let me just show you how the scale looks like. The scale will have, we did not cover this one here. We are in the process in the lecture to just finish up this chapter here. pH from 0 to 6, this is acidic. pH 7 is neutral. And then pH 8 to 14, that's basic. Now, what you have to do if you have a pH that's fractional, sometimes the litmus paper you can see in between color, and then estimate in between color, and or if you have the pH meter will give you a very good decimal value. So suppose I have the pH is 4.6 and the pH is say 6.4 and the pH is 6.5. Now you tell me what is the acidity and basicity of this solution. This is what? Somebody, this acidic, correct? According to whatever we have, this is acidic here. This is acidic, perfect. How about 6.4? 6.4 acidic. Everybody said acidic? Yes, because 0.4 is not 5 and above. 0.4 is not 5 and above. You have to watch for this. So this is still acidic because of the fact that the 4 is not 5 and above. How about 6.5? This one is what? 7. This is 5 here. This is 7. This one is neutral. So you have to watch for the litmus paper will give you 2 colors. The color will be looking in between colors, and then you can estimate 6.5, 6.4, and if we have a pH meter back there, so you can get the idea. But if it's 5 and above, you round it to the next value. Okay, guys. The same token we can see. Can I take this one out? I will take this one out. I'll show you another range here. How about this one here? The pH is 8.9. The pH is 7.4. The pH is 7.8. The pH is 0. So, what you can tell me about this? pH is 8.9, is basic, acidic, or neutral. What is this? That's basic, correct? Perfect. How about this one here? That's neutral. Perfect. How about here? This is 8, correct? And this is 4. Always look at after the decimal value. This is 8. So that's 7.8. That's 8. That's basic. How about pH 0? Acidic. So now you have to know that's the pH, the extreme cases. That's always speak about aqueous solution. pH 0, most acidic. And pH 14, most basic. Okay, guys. So we'll have we'll do some calculations here. So we'll talk about the buffer, and then I will go and look at the what they call it. I will look at the experiment itself. The experiment should not take then. I have for you the results already. Without even doing the experiment, I can predict the values where they can be. So let me take this one here out and then look at the buffer. So if I ask myself, what is a buffer? What's the buffer is all about? Buffer. The word here, buffer. Remember, there is a buffer zone and there is a buffer zone. There is a military buffer zone between North Korea and South Korea. Okay, so what is this buffer zone, military buffer zone between the South and North Koreans' land? What's that? Prevention of conflict? Yes, your answer is correct, but the expression is a little bit shaky. So what we say that's a buffer zone is a neutral zone. Not the North Korean will come into it, and not the South Korean will come into it. It's a neutral zone between the 2 countries. It's a border, but it's a neutral zone. Demilitarized, so there is no military inside for both sides. Are you following me here? So it's neutral. And in the same token here in chemistry, we have the same thing. Buffer solutions, those solutions here, buffer solutions always resist the change of the pH. So the pH will remain neutral. Not neutral in the sense pH 7, no, will be unchanged, correct? So solutions that keep the pH of solutions unchanged. Not a catalyst, but I'll show you how we prepare them. You can prepare those at home as well. So you can prepare those at home. So solution that keep the pH unchanged. So that means they resist any change of the pH of the solutions they are put in. The pH of the solutions they are put in. So if we want to keep the acidity, the basicity of any solution unchanged, you add this buffer, correct? So what are those buffers here? The buffers are made of weak acid and its conjugate base. Let me see here. Here it is. Takes one out here a little bit. So what's happened here is, let's look at this. Buffers are made of weak acids, plus their salts or conjugate bases. This is the salts of the weaker or the weak acid, or they are made of weak base with their conjugate acids. Weak bases, acids here, acids, correct? So if you look at this, and those are salts of the weak bases. So salt of weak bases. So let me give you an example. If I have, and you tell me if we have a pair of those acids or base. I have ammonia and I have ammonium. This is one. I have, correct? I have carbonic acid. I have hydrogen carbonate. Okay? I have hydrofluoric acid and the fluoride ion. So the combination of a base, which is conjugated acid, correct, is a buffer. An acid which is conjugated base, this is an acid, carbonic acid. This is a conjugated base, the hydrogen carbonate or bicarbonate. This is hydrofluoric acid. Bless you. Hydrofluoric acid is weak acid. Its conjugated base is the fluoride ion. Okay? So, same token, I can add here another one, phosphoric acid. Correct? So this is phosphoric acid, and I will add to its conjugated dihydrogen phosphate conjugated base. Those are the buffer. This is number 4. Now, how about if I will add something looking like this, and you tell me if it's a buffer or not. So here it is. How about if I will say to myself, let's make a buffer made of HCl and Cl minus. Is this a buffer? How about if I will make it? So here it is. How about this one here? Are those two buffers or not? What do you think? This is an acid. This is conjugated base. This is an acid. This is conjugate base. This is a base. Correct? This is a base. This is a conjugated acid. So, the opposite. So, what do you think is this? What do you think is happening? Are those our buffer? Yes or no? Everybody? Yes or no? This is not a buffer. Why? HCl is strong acid. HCl is strong acid. Correct? Sodium hydroxide is strong base. So strong acid, strong base cannot form. They cannot form a buffer solution. You have to have a weak acid and weak base, which is conjugated acids or bases. So how we do this one in the lab? So the question is about over how it's not part of the lab, but I want you to be interested in how you make a buffer. Well, it's very easy, correct? So if you have hydrofluoric acid, for example, or carbonic acid, for just an example here. This is carbonic acid. You'll add sodium hydrogen carbonate to it. So, and then if you put the equation here, carbonic acid aqueous in H2O, of course, will give you, the carbonic acid will give you H3O plus, correct? And if you just, we'll take the H2O out so you're not confuse yourself with this. So here it is. Take the H2O out. It's an aqueous solution anyway. So, but this one here will dissociate in H2O to give you hydrogen carbonate and H plus, correct? And then what will happen, this is sodium carbonate. You have to have the ratio. So this is K of the Kc of the buffer. The Kc of the buffer here is Kc, somebody will tell me, H plus hydrogen carbonate. Just to let you know how you can solve this one, H2CH3. So you will see that the ratio here is your buffer ratio. The conjugated acid, the acid to conjugated base, that's the ratio. Kc is from literature, is known. This is known here. So you can determine the pH from here. Are you following me here? You can determine the buffer pH from here. So the ratio, so here it is. The ratio of the conjugated acid here, conjugated base here to the acid here, this is the buffer, and this determine how the buffer is good or not good, the buffer. So that's what we mean by you have the conjugated acid with its conjugated base or a conjugated base with its conjugated acid. And this ratio is crucial, and that's what really maintaining the pH, which is here. From there you get the pH. Maintaining the pH constant is not really change. Now, we will add today just 3 drops. How about if I add 100 drops or a couple milliliters? Do we have a buffer? No. There is something called buffer capacity. The buffer capacity is the amount. This is the ratio here. This is the ratio. If you have this ratio is overwhelmed by the amount of the acid you are adding or the base you are adding, then there is no more buffer. The solution will turn to be acidic, depending on the amount of acid, or basic, depending on the amount of the base. So that's just lecture stuff, but at least you know that's what the buffer is. Now, we will have today, we'll go to the experiment. So any questions so far? Any questions so far? Okay, so it is. We'll have 6 test tubes. Okay, so yes. What's that? That's positive. That's the pH. Here it is. I don't want to go to this, but if you want more information, the Ka or Kc of the acid is H plus. The H, that's the product, correct? over the reactants. Now cross multiply, this is 2 here. Cross multiply, guys. That's carbonic acid. That's inside the soda, correct? That's the fuzzing. Carbonic acid, that's what's inside the soda. When you open the soda, it's fuzzing. That's a fuzzing gas. So carbonic acid, C here. C, no, not C, that's H2CO3, H2CO3. So now, if I cross multiply, now let's do cross multiply here, different color. Cross multiply, what you get? You get Kc multiplied by H2CO3. And this is equal to H plus. And this one here, the bicarbonate. CO3. Let me take this one out here. Yeah, let's wipe this one out and then. So here it is. Cross multiply. You get cross multiply, guys. You get here out of this Kc multiplied by the carbonic acid equal H plus multiplied by the bicarbonate or hydrogen carbonate. So divide both sides by HCO3 minus, divide both sides by H3OC3 minus. So then this cancels with this. So the H plus is concentration is equal to Kc H2CO3 over HCO3 minus. Now this is your H plus. Now the pH here, take the log of both sides. I'm taking the log of both sides. So I have H plus will be Kc H2CO3 divided by HCO3 minus, correct? Now take the log, minus log of both sides. This is minus log H plus. And take the minus log of this one, minus log of the whole of this, the whole thing here. So what you will get here, this is what? This one is our pH. pH will be log Kc or Ka, and then plus the ratio log of the base HCO3 minus divided by H2CO3. This is the equation here. Okay, this is the equation. This is that's higher chemistry, but at least you know you can determine the pH of a buffer. And this is the capacity of the cup this the ratio is very important. If you add too much acid, then you are overwhelming this ratio, and then the buffer is never working. Now, what are those natural buffers? Somebody will tell me. What are those natural buffers in our body? Blood. Blood is a very, very, very sensitive pH. The pH of the blood is about 7.14. I think it's about this. So it's about close to neutral. Now, if you swallow something too acidic, and the pH for some reason or not, if you swallow a poison might be acidic or basic, and the pH is turned to be from 7.4 neutral to 8. For example, this is deadly here, deadly here. Just small tiny digits in the decimal area of the blood, the changing, that can cause death. You can see how the blood is very sensitive for the pH change. So it will resist any change of the pH to the limit. And then when you take a poison that is too acidic or too basic, then you break up the pH of the blood and the person dies from internal poisoning. Are you following me here? Internal poisoning. That's because the blood is no longer a buffer. It cannot resist. You are exceeding the ratio, the capacity ratio between the conjugated acid with the base, or acid with its conjugated base, or the base with its conjugated acid. If this ratio is broken, then the pH is no longer held, and it will be changing. Any type of changing of the pH of the blood cause death. Very sensitive. Now, there are some other stuff in nature, which is carbon dioxide. I mean hydrogen. As we have this in nature here. Carbon dioxide gets moisture, gets carbonic acid. Carbonic acid can give you bicarbonate or carbonate, and that's another buffer. There are many buffers in nature, found in nature, and there are ones we are producing in the lab. What I will do, I will take a sodium, baking soda, solid, and carbonic acid is liquid, mix them together according to the ratio. I can calculate how much I need from this, how much I need the pH to will be of this buffer, and then I'll just add accordingly how many grams of the bicarbonate or baking soda to carbonic acid. That will give me calculate the Kc is here. Kc is given to us from the literature of this acid. Okay. Sometimes some textbook they don't write Kc, they just write Ka, which is the acid itself, carbonic acid. Okay. Kc, carbonic acid. So, well, we went a little bit above and beyond whatever we have planned, but it's okay. That's a good question, though. Okay, guys. So, now to the experiment. As I said, it should not take than 30 minutes. And if you are so tired and you are working, I mean, with your pace and time, maybe 45 minutes. That's max it can take. So, it's a very simple experiment. So we'll have 6 test tubes. 6 test tubes. Here they are, 3 here and 3 here. So you can use your rack here, the plastic rack or the wooden rack. This rack here looks like this. In the past we have wood, but it gets eaten up by the acids and bases. Now we have a plastic rack here. So you see, it has a hole in the bottom here. So, and you put your test tube just inside, 3 here and then the other 3 here. So this is called a test tube rack. In the past we had plastic wooden rack, but we are out of the wooden rack. It's getting eaten up by the acid. So here it is. You number those as follows. Here it is. This is number 1, number 3, number 5. This is number 2, 4, and 6. So even numbers. And this is odd numbers. Okay. So why we are doing this? Well, it turns out to be first, I have to measure the pH of this. This one will have tabor. This one here, buffer solution 3, pH 3. And this is buffer solution pH pH 9. Here's the same thing, pure tabor, nothing inside. This is buffer pH 3, and this is buffer pH 9. Okay, guys, so you can take, as I said, you can take you can take, because you want to see what's the difference. So you can fill those test tubes with 20 drops, 1 ml. I might have a little bit different from whatever, but I want you to see if there is a difference or not. So you fill this one here, 20 drops of H2O, 20 drops, that's 1 ml. That's around 1 ml. And this is buffer solution 3. You take 20 drops, guys, and this one here, buffer solution, 20 drops. And here's the same thing, 20 drops. 20 drops. So, as I said, don't worry about the amount, but I want you to see something. I want you to see, let you to see something here. So now, those three ones here, you take those here. All those three here. First, I will measure the pH of them by themselves. Correct? First, pH of them by themselves. All those, you run the pH using litmus paper. The litmus paper, it has about from 0 to 14. I can show you the color of it. So you measure the pH without any addition inside those solutions, and the same thing with this. So in this, then, after the second step is to add to all those here 3 drops of sodium hydroxide. In those here, you will add 3 drops of HCl. The molarity is very dilute. It's not 0.1 molar, 0.1 molar. So first, you'll have 6 test tubes filled with about 1 ml, 20 drops of the first test tube, labeled number 1, and the 3 and 5. Those are for sodium hydroxide. This side is sodium hydroxide side. This is sodium hydroxide. This side here is HCl side, 2 and 4 and 6. So you measure the pH of all those 3. Now you don't have to repeat this one here because you have already, when you add those solutions 2, 4, 6 pure, you don't have to repeat because that will be the same pH you have already measured in 1, 3, 5 without the addition yet, without the addition there. So now you have measured the pH of 1, 3, and 5 without any addition. Then you will say the same pH will be 4, 6, 2, and test tube 2 and 4 and 6. Now, for the test tube 1 and 3 and 5, the odd numbers, you'll add for each one 3 drops of sodium hydroxide. The molarity of sodium hydroxide is very dilute, is 0.1 molar. For 2 and 4 and 6, you'll add 3 drops of HCl. Now, every time you will see the litmus paper, what is your pH? So that's all. That's the whole experiment. That's the whole experiment. How many minutes you can do this? Less than 45 minutes, I hope. Because I wanted to catch, today is an extra credit outside. Today is an extra credit outside. So any question about this? We are not done yet. I want you to do some calculation with me. So here it is. Hold on. So hold on. Now you tell me here where we can expect. Okay, here it is. Can you see this one here? Maybe I will make it bigger here. So let me make it bigger here. Maybe. So here it is. Okay, guys. So now, what you can tell me about the test tube number 1? It has only what? Let me see here. It has H2O, correct? Pure H2O. So we have 6, correct? So let us see what we can do with them here. I'll give you the data, but I want you to do for me your values, correct? So test tube 1, it has H2O, correct? 1, and then 3, 1 and 3 and 5, correct? 3, it has buffer 3, pH 3, and then 5, buffer 9. When I say 9, that's pH 9. Then I have here, guys, test tube number 2, H2O. 4 is buffer 3, and 6 is buffer 9. Now, what do you think the tap water pH? Just estimation. What will be the pH of tap water? Will be exactly neutral? What's that? You will test it yourself. Well, it will not be neutral because it should be neutral, but because they are using exchanger to get all the ions out, deionize. They call it deionize, to take all the ions out. So it will be around 6. So it's a little bit mild acidic. So tap water is a little bit acidic. Whatever left over of the cleaning acid, they are using HCl to clean up to deionize, to clean up the H2O from all the whole thing. Is coming from the DeKalb County water facilities. So they clean up the those cellulites or those filters, and then with the time there will be always part of the solution there. The tap water is a little bit acidic, correct? The only one the pH is really 7 is distilled H2O. So we have two things here: deionized H2O, and we have distilled H2O. This one is mild acidic. This is absolutely neutral. So this is pH 7. This is pH here around 6 to 6.4. It's acidic, mild acidic. So we have two types of H2O. Correct, guys? So now the one you have in the bottle here, that's not deionized. That's not distilled. That's distilled H2O. You measure the distilled H2O. That's pH 7. That's neutral. The distilled, and it has no taste. Correct? It's like if you have drink the distilled H2O, it has no taste, and it's not healthy. Why is not healthy? Distilled, if you drink every day distilled H2O, what will be? You are dehydrating yourself from all the electrolytes, from all the ions. Our body needs a lot of ions, and that's what the first patient in the emergency room, what they do. The IV bag, what's inside the IV bag? All these electrolytes, all these ions. Iron, zinc 2, iron 3 ions. You have sodium plus 1 plus, magnesium, calcium, potassium, bunch of ions the body needs to function very well. Magnesium. So, and distilled H2O, you strip all this H2O from all the ions, and that's not healthy. If you have this one here, you drink this one here, you will get even if you are young, like 10-year-old, you will get first magnesium is controlling the memories. So you lose your memory, and then you will be like Alzheimer. You will not know nothing about what you were and what you will be, and that's what happened. Magnesium is controlling the amount. Sodium and potassium, our muscles are controlled by the ratio of sodium in, potassium in, sodium out, potassium out. So that's what It's not healthy. You don't drink really distilled H2O, correct? Deionized H2O, that's the mild, it's acidic because of the cleaning, but it has all the ions are there. All the tap water has all the ions is there. So, but in some instances, we don't need those ions in some experiments because they are interfering. So we use distilled H2O. So the tap water by itself, I said mild acidic, correct? Deionized. Now, when you add, we said one, it is, let me write it in red. Red here, red here, red here. Those three red here, 1, 3, and 5, you will add to them 3 drops of what? Of what, guys? Sodium hydroxide, correct? And from the other side here, 2, and 4, and 6, 2, 4, and 6, you will add to them 3 drops of what? Of HCl, hydrochloric acid. So when you add to the first one you add sodium hydroxide, the pH will be acidic or basic? You don't have anything, so the pH will be what? The pH will be, let me just switch. Let me switch here, guys. The pH is 6. When you add sodium hydroxide to it, the pH will be around 13, 12, 13. So between 12 and 13. So will be around, because that's sodium hydroxide, so will be around 12 to 13. So when you add the buffer, if the buffer is working, if the buffer is 3, there should be no change. The pH is 3 when you add your sodium hydroxide. When you add to the buffer 9 sodium hydroxide, it should read 9, no change. Okay, guys? Now let's do the addition here with HCl. If I add HCl to the whole thing, oh, here you did not tell me that's wrong here. That by itself is 6, correct? By itself, without no addition. But then here 12, yeah, that's correct, that's correct. So here it is blue. So when you add H2O to HCl, the pH will be what? Somebody will tell me? Acidic maybe? 3 to 4 something? 3 to 4. You add to H2O. If you have a good buffer, this one should not change, 3. If you have a buffer, this one should be what? 9. And this one here, I'm wrong. Nobody even correct me here. So here it is. Here it is. We did not finish here for the base, correct? We added buffer, so the buffer is 3 here, and here is HCl is 9. So we mix the colors here, guys. Red is 3, correct? And here is 9. And the blue is, if you have a very good, decent, this is 3. This is 9. So that's the whole thing. That's the whole lab. Did I do the lab? No. I did not do the lab, but that's what I'm expecting to get. If I have a good buffer, it should be something like this. The buffer will not change the pH. So first I run the whole thing by themselves to check their pH without addition. And then when I add, I just record. If I add sodium hydroxide, this is basic. If we add, because I added sodium hydroxide, correct? If I add the acidic, that's I added what? HCl. So and so on. But then 3 and 3 does not change. 9 and 9 does not change. I don't see any changes with the pH buffer when I add the buffer to them, because they will resist any change of the pH. The pH will remain as is. Correct, guys? Even if you add sodium hydroxide or HCl, not that much, 3 drops only. That will not change. Any question? Any question? Any question, guys? Any question? No question. I'll take this one out. Now, I have for you, I put for you here, you see here, in your iCollege, in your Dropbox, there is there's already the data here. Here it is, guys. Can you see it? The data is here already. So the data is here, and I want you to be honest with yourself and see if you can get a little, maybe 6 to 5 or 13 to 14 or 12 to. This is just the pure data without any fractional values, those absolute values. So, but anyway, so if I have a buffer, nothing will change the buffer. The buffer 3, whether you add sodium hydroxide or HCl, here, look at this, whether you add this or this. So that's in iCollege already. I posted this one for you. So that this is, it does not really matter. If you have the pH of a buffer 3, and you add sodium hydroxide, no change. You add HCl, no change. Buffer 9, you add to them sodium hydroxide and HCl, there will be no change. So here is no change because you have a buffer. Okay, and here is no change. So, and then the only change is at the tab, or if you add HCl to it, the pH will be acidic. If you add sodium hydroxide, this one will be basic. So that's this sheet here is already posted for you in the iCollege. Now, any question about this? Any question about this? Let's look at the one here. That will be in the final here, guys. Here it is. That will be in the final. I put some couple questions of those for the final here. So don't tell the secretary I did not tell us. I did tell you. That will be coming. So what are coming? Look at the questions here now. We are interested to see those questions here. We'll do before, because I can let you do experiment in 30 minutes, you'll be done. No, I want you to know how to do this, and you help me to calculate all those. I will blow up this one here first. Let me just take this one out, down a little bit, and make this one here bigger. That's supposed to have questions, but we want to solve as much as we can from it, so we can see. Well, I'll just. Sometimes it's because you are copying and pasting, it's not working. So let me go to layout and then customize my layout. Maybe this one here. And then you can go and then change the font here a little bit. Okay, guys, so okay, guys. The title, the top of the title here, you have the concentration of. Please listen. Don't talk here in between. Your voices overlap my voice. If you have any question, raise your hand. I will be more than happy to address your question. So here is the plutonium ion. We need to calculate the pH and determine whether acidic, basic, or neutral. Okay, so if I have the plutonium ion is 1.0010 minus 3, 1.3.10 minus 3, what will be the pH? Somebody will tell me, somebody will calculate this one here. The pH is minus log 1.0010 minus 3. Correct? So what will be the pH here? So here it is. Let me just maybe take it here and then put Put it aside. I'll put here the value, but I'll put this side here. So here it is. The pH is 10 minus 3. I mean, that's the hydronium ion. Minus log, okay? So that's the pH. Minus log of this. What's the log of this will be? The pH is 3. So here it is. We'll put the pH is 3. Is acidic, basic, or neutral? Is acidic. Now, let me tell you about this. This is your instructor in the lecture will cover it. Since we have how many sig figs here? 3 sig figs. So that the value after the digits, you don't care about the whole value at the beginning. But the digits, you have to introduce yourself to digits. You have to have 3 significant figures. You have to have 3 digits after the decimal. This value is not correct. It has to be 3.000. That's the pH. That's the pH. Why? Because here you have 3 sig figs. This is unique of the logarithm of the pH. 3 sig figs, we don't care about this. This is the last thing we care. We care about decimal. We have to introduce ourselves to the decimal, and it has to be 3 digits corresponding to 3 sig figs. So the answer is 3.000. Okay, guys? So, how about the other one? How about the other one? Next one. Somebody will tell me 1 10 to minus. The pH will be what? 3 sig figs will be 11,000. Correct? 10 minus 12. Everybody's following here? So everybody's following. Look at the value here. 10 minus 11. 1 10 minus 11, that's minus log. You take it will be then 11. And then we have 3 sig figs. Then we have to have 3 digits after the decimal. Now, how about 2.41? 10 minus what, 0 or 10? Minus 6? Okay, minus 6. Minus 6, okay, sorry, I can't see it very well here. Minus 6, what's the value here came out to be? Somebody has it? 5.18. So this is 56.18. Again, you have 3 digits because you have 3 sig figs here. 3 sig figs. And therefore you have 3 digits after the decimal. That has to be covered inside the lecture. I cannot go beyond this. Your instructor will help you. Whoever with me, we will cover this one here. We'll cover this one here. We'll do some worksheets as well. So how about the 1.70? 10 minus 4. How much is it? 3.767. 3 digits. Again, we have 3 here. Sig figs. It has to correspond to 3.767 to 3 digits after the decimal. Okay, guys? Is this coming in the final? Yes, that's inside here. I already put this one here. Okay, that will be in the final. But because I did not know if somebody had taken this in the lecture or not, so I might have did not put this one for the exam. I just give you a whole number. I did not really put emphasis on these digits. Now, why? Because maybe some of the instructor will not cover it in your lecture. So, but at least you know that the pH always very sensitive to a number of sig figs then represented in the digits after the decimal, after the whole number. Correct? So, now, any question about this, guys? Any question? Let's go for the second one. Let's go for the second one. So, let's go for the second one. Oh, we did not finish. We did not finish. You did not tell me that we have finished. So, 11 is what? Basic. This one is what? Acidic. Correct? Because this is 6. 6 is still acidic. And this one is acidic. Okay, that's good. We are done now. We are done. So, um, any question about this? Any question about this, guys? Any question? So, yes. Any question? No. Okay. Let's take the second one, because I can't tell you go home and then you don't know what's going on, clueless about this, and it will come in the exam. So next week, as I said, there will be a review. It's optional. You can come. You don't come. It will be registered there. It will be recorded, and we'll go study guide our review. Correct. So here it is. So now you tell me 3.66. What is the value of the first of all, let's this column here, acidic, basic. It is. So the 3.66, acidic, basic, or neutral? Come on, guys. What's that? Acidic, correct. 10.00, basic, correct. 13.50, 7.00, neutral. Now, how in the world we have to get the plutonium concentration? Well, it turns out to be the pH is minus log, correct, hydronium ion. If you remember from the 8th grade, I think I remember, 8th grade or 9th grade math, correct? If I have something look like this, pH minus log x, and I want to get the x, what's the anti-function of log? What we can use? What's the anti-function of log? Come on, that's 8th grade. I remember my kids. Remember about 8th to 9th grade. I'm not sure what's 8th or 9th grade, but that's what's the anti-function? What's that? Exponential of 10. 10, the minus here is minus. And then the value here, minus pH. Okay, so here it is. This one will be, our X will be hydronium ion. Okay, guys, our X will be our hydronium ion, H3O plus. So the first one here, I have 10 minus 3.66. So what is the value here? What's the value? Somebody has it? Minus 366. So what's the value here? 0.0. How much? 10 minus 3.660000. No, that can't be. Somebody will give me another question. Okay, that's we are talking, not 000. No, we said how many digits we will have, correct? So how much is it? 0, 0? 0. How many zeros after the decimal? 3, okay. And then what? 2187? 21874. Now, I would like this one here to have it exponential, correct? So I can say this one here will be, let's put it here, 0.00021874. 7878. Okay, 7878. So I want to have it in the scientific notation so I can keep track on it. So it's up to me whatever I want to do. So I would say 2.1878. What is the decimal? I'm going to the right, correct? So it will be negative. Negative what? How many I went? 4 digits. 1, 2, 3, 4. Perfect. So the hydronium ion is 4. How many digits after the decimal? This is 366. I have to have how many after the decimal? 3. So the answer is 2.18810 minus 4. Always put your values in the what they call scientific notation. Okay, guys? So this is the first one. So this one here, we'll take it as, take this one here and put the value here. So the value will be 2.18810 minus 4. How about the second one? The second one is easy, correct? 10 minus the pH. So it will be what, guys? Will be what? This the pH. Instead of having this, we are taking this one out. Let me just do it another color. Instead of this, will be minus 10, correct? Minus 10. 10 minus 10. However, is 1 there, but I will write, because how many significant figures I have? How many? 10.00, that's 4. So I will write it 1, 0, 0, 0, 0, 10 minus 10. Okay, guys? How many I have here? 4 digits. Why? Because this is for significant figure. Okay, guys? 1, 0, it's 1, but you have to satisfy the rule of the pH. Okay? So how about the next one? Let's take the next one, the third one. I can't let you go without knowing this. You have to know this because if you get that in the final, you'll be upset with me. Oh, Dr. Tay did not cover this. I'm covering this for the final. Next week, we'll even cover more examples. So let's do this. Now I'm taking this one here now out. This one is 13.50. 10 minus 13.50. Those are 4 digits. So how much is it? 3. Negative 14. Thank you. 3.162. 3. You have 4 sig figs. We have to have 4 sig figs. Correct? 3.162310 minus 14. Okay? So, and the last one is 3 sig figs. 7. Okay? 1, 2, 3, 10 minus 7. Okay, guys? So, maybe I have to put this one here. In a way you can see it. So, you tell me if I have it correct or not. So here it is. How much was it? 3.162 what? 3, 10 minus 14. Okay, guys. Now you have the post lab almost done for you. This is because it's coming in the lecture, final exam ACS, and it will come in the lab. So I'll stop recording here and let's finish up the experiment, and then we can catch our event back in the student center. Okay, guys? Thank you very much.